let's get started. So welcome to the next lecture about exploiting buffer overflows. So today what we're going to do is we're going to finish up our discussion about baggy bounds, and then we're going to move on to a couple of other different techniques for protecting against buffer overflows. Then we're going to talk about the paper for today, which is the blind return-oriented programming. So if you were like me when you first read that paper, you kind of felt like you were watching like a Christopher Nolan movie at the beginning. It was kind of like mind-blowing, right? So what we're going to do is we're going to actually step through how some of these gadgets work, right? And so hopefully by the end you'll be able to understand all of this sort of high-tech chicanery that they're doing in the paper. So first of all, like I said, let's just close up with the baggy bounds discussions. Let's go through a very simple example here. So let's say that we're going to define a pointer called P. And let's say that we're going to give it allocation size of 44. And let's also assume that the slot size equals 16 bytes, okay? So what's going to happen when we do this malloc up here? So as you know, the baggy bound system is going to pad that allocation out to the next power of 2. Right? So even though we've only allocated 44 bytes here, we're actually going to allocate 64 bytes for this pointer up here. And so also note too that since the slot size is 16, how many bounds tables entries are we going to create? Well, we're going to create the allocation size, right, which in this case is 64, divided by the slot size, which is 16. So in this case, we'll create 4 different bounds table entries for this thing right here. And each one of those entries is going to be set to the log of the allocation size, which in this case is going to be 6, right? Because the allocation size is 64. Okay? So far so good. Then we're going to define another pointer called Q, and we're going to set it equal to P plus 60. So what happens when we do this? Well, note that strictly speaking, this access is out of bounds, right? Because this was only allocated 44 bytes of memory. But of course, the way that baggy bounds works is that it will actually allow accesses that are out of bounds if they stay within that baggy bounds. So even though, strictly speaking, the programmer probably shouldn't have done this, this is actually going to be OK, right? We're not going to raise any flags or anything like that. Now, let's say that the next thing we do is we define another pointer, which is going to be set equal to Q plus 16, right? Now, this is actually going to cause an error, right? Because now Q is at an offset of 60 plus 16, which equals 76. So this is actually 12 bytes away from the end of that baggy bounds, okay? And that's actually greater than half a slot away. Right, so if you remember, the baggy bound system will actually throw a hard synchronous error if we get beyond half a slot from the edge of that baggy bounds. So this will actually cause the program to fail. Right? This will actually make it stop. Now, let's imagine that we didn't have this line of code in the program. Okay? So we had these two, but we don't have this one. So what if we, instead of doing this line, did something that looks like this? We declare another pointer. Let's call it S. And we set it equal to Q plus 8. Now, in this case, the pointer is going to be at 60 plus 8, which equals 68 bytes away from P. Right? So this is only 4 bytes beyond that baggy bound. So this will not actually cause an error, even though it is, strictly speaking, out of bounds. But what we will do here, though, is set that higher order bit on the pointer, right? So that if anyone subsequently tries to dereference this thing, it's going to cause a hard fault at that point. Right? And then let's say the final thing that we do is we declare another pointer, T, which is going to equal S minus 32. So what happens here is that essentially we've brought this pointer T, it is now back in bounds. Right? So what that means is that even though this guy was out of bounds, now we've sort of gone back into the original allocated region that we originally created up here. So as a result, T will not have that higher order bit set. And so you can dereference T and everything will be fine. Right? So does this all make sense? This should be fairly straightforward.
The difference between R and S, how did you know that R is, or how
Ah. So note that, like up here, when we create R, we can basically interpose, we have that instrumented code that's going to be looking at all of these pointer operations, right? So basically we can tell is that we know where P is going to be. We know where Q is going to be, right? And we know that Q is within those baggy bounds. And so when we do this operation here, the instrumentation that baggy bounds adds will be able to say, aha, well I know where that source point was coming from. And then if you look at this offset here, you determine it's more than half a slot away from the original slot size. So the basic way to think about it is that as we're doing these pointer operations, we're sort of looking and saying, have you gone out of bounds, have you gone out of bounds, yes or no. At some point you're going to have some operation that's going to involve a pointer that is either inbound or in the baggy bounds, and then some thing over here that makes it go out of bounds. Right? And so at that moment, right when that happens, that's how we know that something chicaneous has arisen. All right, so hopefully that should all make sense. And so just to very briefly review the homework question. So hopefully if you understand this, the homework question should be pretty easy to understand. So we had a character pointer, we now had 256 bytes to it. And then we declared character pointer Q. That's going to be equal to that pointer plus 256. And then we essentially try to reference this pointer. So what's going to happen? Well, note that this is an exact power of 2, right? So there's not actually any bagginess in the bounds, right? So when we do this right here, this makes Q point to 1 past the end of those baggy bounds. So just like in this example up here, this line is actually fine, but it will cause the high bit to be set in Q, right? So when we come down here and reference it, then everything blows up, and it's time to call in your insurance agent. So pretty straightforward. Okay, so that's basically 2 examples which give you a flavor for how baggy bounds works. As I mentioned in the last lecture, you don't actually have to instrument every pointer operation if you can use static code analysis to figure out that a particular set of pointer operations is safe. I'll defer a fuller discussion of some of the stack analysis to later lecture, but suffice it to say that you don't always have to have all of this, sort of bitwise arithmetic that you have in some of the cases that we've examined before. And so another question that came up a lot in Piazza was how does baggy bounds ensure compatibility with these pre-existing non-instrumented libraries, right? And so the basic idea behind how baggy bounds does that is that when baggy bounds initializes the bounds table, it's going to set all of the entries to be that value of 31. So remember that the bounds table, each entry represents sort of 2 to the power of that entry, the size of that particular pointer. Right? And so by initializing all those bounds to 31, what this allows us to do is automatically assume that each pointer from uninstrumented code is going to have the largest bound possible, 2 raised to 31. Okay? So let me just give you a very simple example here that will hopefully make this a little bit clearer. So let's say that this over here is the memory space that we use for the heap. And in this simple example, let's suppose that we basically split this memory space up into 2 components. This is the heap that is allocated by the uninstrumented code. And then let's suppose that down here we have the heap that is allocated by the instrumented code. And so what's baggy bounds going to do? So remember, baggy bounds has this notion of a slot size, right? So basically, if the slot size is 16, you only have an entry for every sort of slot of size 16 over here, right? So basically, the bounds table in this case, you can think of as being set up into 2 places. So initially, all of the bounds table, all the entries are initialized to 31. Right? But then eventually, as the instrumented code runs, it's actually going to use the baggy bounds algorithm to set these values to whatever should be appropriate for that particular instance of bound or instance of free, right? So what ends up happening is that if instrumented code gets a pointer that comes from here, then those baggy bounds for each particular pointer are always going to be set to the largest possible value, 231. 2 to the 31, right? Which means that it's going to be impossible for baggy bounds instrumented code to think that you've done an out-of-bound operation with that pointer that's coming from this uninstrumented library. So does that make sense? Right? So the idea is that in instrumented code, we're always going to be doing these comparisons with the pointers. But if we always set the bounds entries for instrumented pointer code to 2 to 31, you can never have a dereference error. Okay, so that's basically how we have this nice interoperability between the instrumented baggy bounds code and between a non-instrumented off-the-shelf legacy libraries. So putting it all together, what does this all mean? So we have this system here, which is nice because it doesn't make the uninstrumented libraries blow up. But one problem is that we can't detect out-of-bounds pointers that are generated in the uninstrumented code, right? Because we're never going to set that high bit, for example, if that uninstrumented pointer gets too big or gets too small or anything like that. So we actually can't provide memory safety for operations that take place in the uninstrumented code. You also can't detect when you pass an out-of-bounds pointer from instrumented code to uninstrumented code. Something insane can happen, right? Because remember, if you have this out-of-bounds pointer from the instrumented code, it has that high bit set to 1, right? So it looks like it's super ginormous, right? Now we know if we just kept that pointer in instrumented code, we might clear that flag at some point if it comes back in bounds, right? But if we just pass this ginormous address to uninstrumented code, then who knows? It may try to dereference it, it may do something crazy. It may even bring that pointer back in bounds, but we would never have an opportunity to clear that high bit, right? So you could you still may come up with some interop issues there, even if we use this scheme over here. Okay, so that's essentially how baggy bounds works on a 32. Oh, you have a question?
Yeah. So if you have uninstrumented code and you need to allocate memory, is it using the same malloc that the instrumented code is using, or?
Yeah, so it's a bit subtle. So like in this case here, it's like very stark what's going on, right? Because there's just sort of two regions, one of which is used by each set of things. So it actually depends on the vagaries, like how code's getting linked and stuff like that. You can also imagine that, like in C++ programs, for example, you can define your own allocator, right? So it kind of depends. The devil's in the detail.
I guess I'm wondering is so if they're the same or different. If they're the same, how does the allocator know whether or not set something 31 or just?
Yeah. So at the lower level, typically the way that these allocation algorithms work is that you call the underlying system, call it break or something like that, to sort of move a pointer up. So you can imagine that if you have multiple allocators all trying to allocate memory, they each sort of have their own chunk of memory that they reserve from themselves, basically, right? And so in real life, it may be sort of more fragmented than this. That's essentially high level how it works. Okay, so this was baggy bounds on a 32-bit system. So as you all know, 64-bit systems are these days. So how does baggy bounds work on those systems? Well, in those systems, you can actually get rid of the bounds table because we can actually store some information about the bound in the pointer itself. So imagine we're going to look at a regular pointer in a baggy bound system. So we can use it like this. So we can, if the pointer is inbounds, we can basically just set the first 21 bits to 0. We can put the size in these 5 bits here. And once again, this is representing the log base 2 of the size here. Right? And then we have here in the remaining 38 bits, just the regular address bits. Now the reason why this doesn't massively curtail the address size that the program can use is that a lot of these sort of high order bits, the operating system and or the hardware doesn't let applications use for various reasons, right? So as it turns out, we're not dramatically shrinking the amount of memory that the application can use in the system. So this is what a regular pointer looks like. Now what happens when we have one of these out-of-bound pointers? Well, in the 32-bit system, all we can do basically is just set that high order bit and then just hope that that thing never got beyond half a slot away from its base. But now that we have all this extra address space here, we can actually put the out-of-bounds offset directly in this pointer. So we can do something like this. So we can have 13 bits here for the offset, right? The out of bound offset. How far away is this out of bounds pointer from the place where it should be? And then once again, we can put the actual size of the reference object here. This will be 0 once again, and this will be the real address space here. And so this may be reminiscent to you of some type of like fat pointer representation. But there's a couple of advantages here now that we're living in the 64-bit world. So first of all, you'll note that these tag pointers, these are the regular size of a regular pointer, right? Pointers are still just 64 bits wide in both of these setups, right? And so that's nice because that means, for example, that reads and writes to that pointer are atomic, unlike in traditional fat pointer world where we actually have to use multiple words to represent that fat pointer. So that's nice. And also note that we can, trivially pass these things to uninstrumented code because they look and are the same size just as regular pointers. Right? We can put these things in structs, for example, and the size of those structs won't change. So this is very nice if we live in a sort of 64-bit world. So does that all make sense?
So why are there 8 0 bits in the out of bounds pointer there, where like the 5 size bits previously were?
So you're talking about down here?
Yeah, is there a reason that we can't just put like 5 or like 6 0 bits there and have more bits for the offset? Like why is the number 8?
So I think, in some cases, there are certain alignment issues that we have to work with. But the alignment issues mainly just deal with sort of the bits that are higher here. I don't think in principle there's any reason why you couldn't do some of these things or not. But so there may be some hardware issues that I'm not thinking of right now that mean that some of these bits have to be 0, otherwise the hardware's going to, cause problems. Any other questions? Okay, so next thing you might be wondering is, can you still launch buffer overflows in the baggy bound system? Obviously, because we gave you another paper to read, so clearly this thing doesn't solve all the problems, right? So one problem that you might run into is that if you have uninstrumented code, once again, we can't detect any problems in uninstrumented code. You could also encounter memory vulnerabilities that come about from the dynamic memory allocation system. So if you remember last lecture, we looked at this weird sort of free malloc sort of weird pointer thing that took place. Baggy bounds won't necessarily prevent you from some of that stuff. We also discussed last lecture where the fact that code pointers do not have bounds associated with them, right? So imagine that you had a struct, it has a buffer at the bottom, it has a function pointer up top. If you have a buffer overflow into that function pointer, right? Let's say that buffer overflow is still within the baggy bounds. Okay, so you've overwritten that function pointer. When we try to execute that function pointer, it can be pointed to some controller, attacker controlled piece of memory. Okay, and bounds won't help with that because there's no bounds associated with function pointers. And so, in general, what are the costs of baggy bounds? So there are essentially 4. So the first cost is space, right? So if you're using a fat pointer, obviously you've got to make pointers bigger. But if you're using the baggy bounds system that we just discussed, you've got to store the bounds table, right? And so the bounds table has that slot size, which allows you to control how big that bounds table is, but still, you may end up using non-trivial amount of memory for that. You've also got the CPU overhead of doing all of the pointer instrumentation, right? So for every, or close to every pointer thing that you do, you've got to check these bounds using sort of those shift operations and things like that. So that's going to slow your program down. There's also this problem with false alarms, right? So as we discussed, it may be the case that a program generates out-of-bound pointers but never tries to dereference it, right? Strictly speaking, that's not an issue, right? But baggy bounds will flag the creation of those out-of-bounds pointers if they get beyond a half a slot size, at least in the 32-bit solution, right? And so what you'll see with a lot of security tools is that false alarms really reduce the likelihood that people are going to use your tools, right? Because in practice, we would all hope that we care about security, but actually what do people care about? They want to be able to upload their silly Facebook photos and like things, and they want to be able to make things go fast and stuff like that. So you really want your security tools to probably have less coverage of finding bugs, but actually have 0 false alarms, as opposed to catching all types of security vulnerabilities, but then maybe having some false alarms that are going to irritate developers or irritate users. And the other cost that you have for this, finally, is that you need compiler support. right, which can actually end up being non-trivial because you have to go in there, you have to add all the instrumentation for all the pointer checks and so on and so forth. So those are basically the cost of these bounds checking approaches. So that concludes the discussion of baggy bounds. And so now we can actually think about 2 other mitigation strategies for buffer overflows. They're actually much simpler to explain and understand. So one of these approaches is called a non-executable memory. And the basic idea is that the paging hardware is going to specify 3 bits for each page that you have in memory. Read, write, and execute. Right? Can the program read that memory, write to it, execute it? The first 2 bits are old, right? They've been around for a while. That last bit is actually a fairly new construction. And so the idea is that you can actually make the stack non-executable. Right? So if you make the stack non-executable, that means that the adversary can't run code just by creating that shell code and then sort of jumping to someplace in that buffer. And so what a lot of systems do is they actually specify a policy like this. So write exclusive or X, right? Which means that if you have a particular page, you can either write to it or you can treat it as executable code, but you cannot do both. Okay, and so that once again is going to prevent the attacker from just putting executable code in the stack and then going straight to it. So this should be pretty straightforward, right? So we've removed at the hardware level this attack vector of the attacker putting executable code in the stack. So what's nice about this? Well, potentially this works without any changes to the application, right? This is all taking place sort of at the hardware level and at the OS level, with the OS just sort of making sure that pages are protected with these bits. Okay, so that's very, very nice, right? Because we don't have to worry about this compiler support issue we had over here. The other nice thing is that, as I mentioned in the last lecture, the hardware is always watching you, even though the OS is not, right? So these bits being set over here, they're looked at and verified for correctness, in every memory reference that you make by the hardware. So that's a very nice aspect of this too. Now, one disadvantage of this system, though, is that it makes it harder for an application to dynamically generate code sort of in benign or benevolent cases. And the best example of that is the just-in-time compilers that we discussed from last lecture, right? So how is it that you can go to your web page and your JavaScript code executes fast? It downloads that JavaScript source. It initially probably starts just interpreting it, but then at some point it's going to find some hot path, some hot loop, and then it's going to dynamically generate x86 machine code and execute that directly, right? But to get that to work, you have to be able to dynamically write code to a page, right? So there's some ways you can get around this. For example, you can imagine that the just-in-time compiler initially sets the write bit, and then it removes the write bit, then it sets the execute bit. So there's some ways that you can get around that, but it can be a little bit tricky sometimes. But at a high level, that's how non-executable memory works. Pretty easy to understand.
What is the definition of like executable instruction? So if you change the return address, that's not considered an executable instruction.
Well, basically, can you set like the instruction pointer register to that value, right? In other words, can you, if you have a bunch of memory pages, can you actually set EIP there and actually start executing code from that page? Okay, so that is non-executable memory. And so another technique you might imagine for protecting against buffer overflows is using randomized addresses or address spaces. And so the observation here is that a lot of the attacks that we've discussed so far use hard-coded addresses, right? And so if you think about a lot of the attacks that you've been working on in your lab, how does that work? You open up the program in GDB, you find out the location of some things, then you create some shell code that actually has some hard-coded addresses in there, right? So the idea behind the randomized address space is simple. Basically, you want to make it difficult for the attacker to guess addresses. So there's a couple different ways you could think about doing this, right? So one idea is that you could imagine having stack randomization, right? So imagine that from here to here, this is the entire virtual memory space of the program. right? As we described this stuff to you so far, basically the stack always starts at this particular place up here, always goes down, right? And then the program code's down here, and then the heap always goes up here. And all of these segments, the stack, the heap, and the program code, they all start at a well-known location, right? So imagine, for example, like if my lecture notes here are the stack, you can imagine instead of the stack always starting here at this known location, maybe you start it here, right? Maybe you start it here, somewhere else like that, right? Similarly, you can imagine that maybe the program code, which used to always start down here, maybe we start it up here or down here or something like that, right? And so the idea now is that if you, the attacker, control one of these binaries, you can look in GDB and figure out where all these offsets are, but they're not actually going to help you figure out where those offsets are in the real code that's running on the server, right? So that's the basic idea behind these randomized address spaces there. And so this takes advantage of the fact that a lot of the code that you generate doesn't have to be loaded into a specific place in memory, right? So unless you're writing like a device driver or something like that that maybe is interacting with some hardware that requires, this particular address to be, belonging to this particular buffer so it can copy information in. If you're not doing stuff like that, then typically your code's going to be relocatable. So this approach will work very nicely with that kind of stuff. Once again, the question is, can you exploit this? Obviously, the answer is still yes. Right? There's a couple different ways you can do it. As we'll discuss later today in the Brot paper, the attacker can actually extract randomness. Right? And so in general, that's how you defeat all these randomized approaches. You make them unrandom by either finding out the random seed that the attacker was doing or by somehow leveraging the fact that the attacker leaks information about the randomized locations of these things. And another thing that's interesting is that for a lot of the attacks we've discussed so far, we've basically been using these sort of hard-coded addresses. But note that the attacker may not necessarily care about jumping to a specific address. Right? There's this attack called a heap attack, which is actually pretty hilarious if you're a bad person, I suppose. So the way that this heap attack works is that the attacker essentially just starts dynamically allocating a ton of shellcode and just stuffs it randomly in memory. Right? This is particularly effective if you're using like a dynamically high-level language like JavaScript, let's say. So the attacker can just sit in a tight loop and just generate a bunch of shellcode strings, right? And you just fill the heap with all these shellcode strings. Right? Now the attacker maybe cannot figure out where the exact location is of each of those shellcode strings, but if you've allocated, tens of megabytes of shellcode strings, and then you just do a random jump, right? If you can somehow control one of these ret pointers, then hey, maybe you'll land in shellcode, right? And one trick you can actually use is this thing called no-op sleds, which is also pretty hilarious. So imagine that if you have a shellcode string, then it may not work out if you jump to a random place in that shellcode string, because it may not set the attack up correctly. But maybe this stuff that you're spewing to the heap is basically just a ton of no-ops, and then at the very, very end you have the shellcode, right? This is actually quite clever, right? Because this means that now you can actually goof up the exact place where you jump. If you jump into another one of these no-op things, you just go boom, 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 then you hit the shellcode, right? So it's like these are the people that you probably see on the T. They're inventing these types of things, right? So this is a problem. So that's another way you can get around some of this randomization stuff, just by making your code sort of randomization resilient, if that makes sense. Okay, so that's basically a discussion of some of the types of randomness you can use. There are also some other wacky ideas that people have had too. So imagine that when you want to make a system call, for example, you use the syscall libc function, and you basically pass in a unique number that represents the system call that you want to make. Right, so maybe fork is 7 and maybe sleep is 8, something like that, right? So what that means is that if the attacker can somehow figure out the address of that syscall instruction and jump to it somehow, he or she can actually just supply the system call number that they want to invoke directly, right? So you can imagine that each time the program runs, you actually create a dynamic assignment of syscall numbers to actual syscalls, right, to make it harder for the attacker to guess stuff. There's even some very avant-garde proposals to change the hardware such that the hardware actually contains an XOR key that is used to dynamically XOR instructions, right? So imagine every time you compile a program, all the instruction code is actually XORed with some key, right? That key is put into that hardware register when you initially load the program, and then whenever you execute an instruction, the hardware automatically XORs it before you continue executing that instruction. Right? And so what's nice about that is that now, even if the attacker can generate this shellcode, the attacker doesn't know that key, right? So it's very difficult for the attacker to figure out what exactly to put into memory.
But if you can read the code and sort back the instruction and move the key.
Oh yeah, this is always a canonical problem, right? So it's like, but if someone does this, so that's exactly right. So this is somewhat similar to what happens in the BROP attack, where ostensibly we've sort of randomized where locations are, but the attacker can do probes, right, and kind of figure out what's going on. So you can imagine too that, for example, if the attacker knows some subsequence of code that he expects to be in the binary, you can imagine just sort of trying to XOR the binary with that known code, trying to extract the key. I mean, there's a lot of evil in the world, so you're exactly correct about that. Okay, so that's essentially a discussion of all the randomization attacks that I want to discuss today. So one thing to talk about before we get to some of the return-oriented programming stuff is you might wonder which ones of these defenses are actually used in practice, right? And so as it turns out, both GCC and Visual Studio, they both enable stack canaries by default, right? So that's very popular. That's very well known in the community. If you look at Linux and Windows, they can also do things like non-executable memory. They can also do things like randomize the address space. So that's also very popular. The baggy bound stuff, however, is not as popular. And that's because of some of these costs that we talked about over here, in terms of memory overhead, CPU, the false alarms, and so on and so forth. So that's basically a survey of sort of the state of the art in trying to prevent these buffer overflows. So now we're going to talk about this return-oriented programming stuff. So what I've described to you so far today in terms of the address-space randomization and the data execution prevention, that's the read, write, and execute bits that I just described. Those things are actually very, very powerful, right? Because the randomization prevents the attacker from actually understanding where hard-coded addresses are. And the data execution prevention says even if you can put shellcode into the stack, then the attacker can't just jump to it and execute, right? So at its face, that seems like, man, you've really made a lot of progress towards stopping these attackers. But of course, there are these hackers out there who spend all their time thinking about how to ruin our lives. So what's the insight behind return-oriented programming? The insight is that what if instead of the attacker being able to generate just sort of new code at attack time, what if the attacker could string together pre-existing pieces of code and then sort of string them together in deviant ways, right? And we know that the program contains a ton of code already, right? So hopefully, or unhopefully, depending on which side of this you're on, if you can find enough interesting code snippets, you can string them together to basically form like this Turing-complete language where the attacker can essentially do whatever the attacker wants to do. So that's the insight behind return-oriented programming. So to understand how this works, let's look at a very simple example that will initially start off very familiar, right? But then it's very quickly going to descend into madness. So let's say that we had the following program. So we have some function, and conveniently for the attacker, it has this nice function here called run shell. So this is just going to call system. It's going to execute then/bash, and then be done. And then we've got the canonical buffer overflow function down here. Basically, this thing is going to declare a buffer, and then it's going to use one of these unsafe functions to fill in bytes in the buffer. Okay, so we know that this can be overflown. Okay, this is old news. Now, what's interesting is that we have this function up here, run shell, but it doesn't quite seem to be accessed in some direct way, based on this buffer overflow. So how can the attacker invoke this run shell command here? Well, the attacker can do a couple things. So first of all, the attacker can disassemble the program, run GDB, find out the address of this thing in the executable, right? So you all should be very familiar with doing those kinds of things through the lab, right? So that's the first thing the attacker can do. And then during the buffer overflow, the attacker can essentially take that address, put it in the buffer overflow that's generated, and make sure that the function returns to run shell. So just to make that clear, let's draw that over here. So you have a setup that looks something like this. At the bottom, we have the buffer that's being overflowed. And then up here, we have the saved break pointer. Up here, we have the return address for process message. And so remember that the new stack pointer will be here initially when we start executing the function. This is the new break pointer. This is what the stack pointer used to be. And then we've got like some break pointer up here for the previous frame. Okay, so this should look pretty familiar. So basically, in the attack, like I said, we've used GDB to figure out what the address is of run shell. So in the buffer overflow, we can essentially just put the address of run shell right here. Right, so this is actually a pretty straightforward extension of what you already know how to do. Right? So basically it's saying if we conveniently have a command that runs a shell, if we can disassemble the binary, figure out where that address is, we can just put that in this overflow array that we have here. So that should be pretty straightforward. Does that make sense? Okay. So this was a very sort of childish example because the programmer, for some crazy reason, has put this sort of low-hanging fruit here. So as an attacker, this is like Christmas coming early, right? Now, it may not be the case that you have something as delightful as this. So what you could have instead is something like this. So let's say that instead of this thing being called run shell, we call it run boring. And then maybe this thing just executes bin/ls, let's say. But let's say that everything is not completely lost because we actually have a string up here that conveniently gives us the path of bash. So what's interesting about this is that we can disassemble the program, find the location of run boring, but as an attacker, who wants to run ls, right? That's no fun. But we do actually have a string in memory that points to the path of the shell. And actually, we also know something interesting too, which is that even though the program isn't calling system with the argument that we want, it is calling system somehow. So we know that system must be getting linked into this program somehow, right? So we can actually leverage those two things to actually call system with this argument here, right? So the first thing that we do is we can go into GDB and we can actually figure out where this thing is located in the process binary image, right? So you just go to GDB, you just type in basically print system, and it'll give you some information about the offset of that, okay? So that's pretty straightforward. You can also do the same thing with bash path, right? You can just use GDB to figure out where this thing lives. Statically declared string, right? So you should be able to find out where that lives. And so once you've done that, now you've got to do something a little bit different, right? Because now we actually have to figure out somehow how to invoke system with an argument of our choosing, right? And so the way that we do that is by essentially faking a calling frame for system, okay? So remember that a frame is the thing that the compiler and the hardware sort of work together to use to implement the call stack, right? So here's basically what we want to do. We want to set up something like this on the stack. Right? So basically, we're going to fake what system would expect to be on the stack, like right before it actually executes its code. So up here we have the argument to system. This is the string that we actually want to execute. And then down here, this is where system should return to when it's done. right? So this is what system expects the stack to look like right before it starts execution, right? It's going to say, this is where I should go in and finish. This is the thing I should consume as my argument, right? In the past, we've been assuming that there were no arguments when you pass the functions, but now this is a little bit different, right? So basically, we just have to ensure that this thing is in that overflow code that we create, right? We just have to make sure that this fake calling frame is in that array. So basically, the way this will work is we will do the following. So once again, remembering the overflow goes up here. So first, we're going to put the address of system here. And then here, we're going to put just some junk return address. Right, this is where system's going to return after it's finished. For the purposes of the discussion now, we don't care what this is. We'll just make this be just some random set of bytes. And then up here, we're actually going to put the address of bash path. Right? So what's going to happen now when we do this buffer overflow? So what's going to happen is that process message is going to finish. It's going to say, OK, hey, here's what I should return to, right? And then it's going to pop the stack, right? And now the system code is executing, right? The system code now sees that fake call frame that we created, right? As far as system is concerned, nothing chicanerous has taken place, right? System will say, here's the argument that I want to execute. It's bin/bash. It's going to execute it, and voila, the attacker has a shell, right? So does this make sense? So basically what we've done is we've now taken advantage of knowledge of the calling convention for the platform to create fake stack frames, or fake calling frames, I should say. And using those fake calling frames, we can actually execute any function that is already sort of linked and defined in the application. Does that make sense? OK. So another question you might have is, what if this string wasn't actually in the program? Now, to be clear, this string is almost certainly in the program. So that's one funny thing about security. There are just all kinds of fun strings that are laying around. You can just go to town all day long. But let's suppose we live in Bizarro world, and this string is not in the program. So does anyone have any ideas about what we could do to sort of get that string to be in the program?
We can put the string on the stack.
Yes, exactly. Don't trust that man. That's what you can do, exactly. So what you can do is actually, for here, have the address of bash path actually, point here, right? And then you put, up here you put, /bin/pat, /0, right? So that's how you can get around. I think I got that map right? Because each one of these is 4 bytes, right? But anyway, so you have the pointer go up here, and then boom, you're done. So now you can actually conjure up arguments just by putting them in the shell code, right? Pretty horrifying. So this is all sort of building up towards the full drop attack, right? But before you can understand the full drop attack, you've got to understand how you can sort of chain together these pre-existing things in the code. All right. So one thing to note is that when I was setting up this return address here, I just said, just put some junk here. It doesn't really matter, right? We just want to get a shell. But if you're the attacker, you could actually set this return address to something that's actually useful, right? And if you did that, then you could actually string together several function indications in a row, right? And that's actually very, very powerful, right? Because in particular, if we literally just set this return address to junk, it may be that when we read from it, the program crashes or something like that. Maybe we don't want that, right? So we can actually start chaining some of these things to do interesting stuff. So let's say that our goal is that we want to call system an arbitrary number of times. Okay, we don't just want to do it one time, we want to do it an arbitrary number of times. So how can we do that? Well, we're going to use 2 pieces of information that we already know how to get. Right? We know how to get the address of system. Right? We just look in GDB and find it. We also know how to find the address of that string bin/bash. But now to actually make this attack work using multiple calls to system, we're going to have to use gadgets, right? So this is getting us closer to what's taking place in the Brock paper. So what we need to do now is find the address of these two opcodes. Right? So what is this? So this is pop into EAX. So what does this do? This just takes the top of the stack, and then it puts it into the EAX register. Right? And what is the ret instruction going to do? It just pops the top of the stack, and then puts it into EIP, the instruction pointer. Okay? So this is what's known as a gadget, right? This is like a small set of assembly instructions that the attacker can use to sort of build these larger, more grandiose attacks. Okay? So how can we find this gadget, right? There's actually like some off-the-shelf tools that like hackers use to find these things. It's not hard to get the binary, right? I mean, essentially you just do a grep for these types of things, right? So it's just as easy to find one of these gadgets, right? Assuming that you've got a copy of the binary and we're not worried about randomization yet. It's very easy to find these things, just like it's very easy to find the address of system and stuff like that. So if we've got one of these gadgets, what can we use this gadget to do? Well, of course, the answer is evil. So what we can do is the following. Let's say that we change the stack so that it looks like this. Right, so the exploit goes this way. And so let's say we do this. So the first thing we're going to put here is the address of system. And then the thing we're going to put up here is the address of the pop ret gadget. Then up here, we're going to put the address of bash path. And then we're going to repeat this pattern. So we're going to put the address of system, the address of the pop ret gadget, and then the address of bash path. Okay, so what's going to happen here now? Now this is going to be a bit tricky, and these lecture notes are going to be up on the web, so you may just want to listen to what's happening, but this, when I first understood this, this was like understanding that Santa Claus wasn't real, right? Okay, so what will happen is, by the way, Santa Claus isn't real. I hope I didn't reveal that for anyone. So what's going to happen? So the buffer overflow goes like puts this in memory. So we're going to start here, okay? So what's going to happen? We're going to return the system, right? The ret instruction is going to pop an entry off the stack. Now the top of the stack pointer is here, okay? So system is going to find its argument here. It's going to execute the shell. Then it's going to finish and return to whatever is here, which is the pop gadget. In executing that return, we change the top of the stack pointer to be here, okay? Now we are in the pop ret gadget, okay? So what is that pop ret gadget going to do? It's going to pop what's on the stack, which is this, okay? So now the top of the stack is here. Then we're now in the ret instruction from the pop ret gadget. What's it going to do? Aha! It's going to call system again, right? So once again, the ret is going to pop this off the stack. We are now in system. Top of the stack is here, right? System is good. This looks like a calling frame to system. System takes the bash path argument here, okay? And then it is going to ret, right? Where is it going to ret to? The pop ret gadget again. So the ret pops the stack. We are now in the pop ret gadget. The ret gadget, the pop ret gadget is going to pop this, so on and so forth. Okay? So clearly we can sort of chain this sequence to execute an arbitrary number of things. Right? And so this, in essence, is starting to get to the core of what return-oriented programming is. Note that we have not executed anything in the stack. right? This is what has allowed us to get beyond those data execution prevention bits, right? Nothing's being executed here. We're just sort of jumping to things in unexpected ways to do what we want to do. Okay? So this is actually very, very, very clever. And so what's interesting is that at a high level, you can think about us, we've now sort of defined this new model for computation, right? So in a traditional non-malicious program, you have the instruction pointer that sort of points to some linear sequence of instructions, and you increment the instruction pointer to figure out what's the next thing to do, right? In essence, what return-oriented programming does is it uses the stack pointer as the instruction pointer, right? So as we move this stack pointer, we're sort of pointing to like other blocks of code that we're going to execute. And then at the end of the gadget, we return back to the stack pointer, which is then going to tell us the next block of code to execute. Okay, so does that make sense? Okay. All right, so that's basically how you can avoid the data execution prevention stuff. That's how you can get around having this, this no execute code on pages. So the next thing that we might want to do is defeat stack canaries. So if you remember, this canary was this value that we were going to place on the stack, right? So you can imagine the canary would sort of go right here, for example, or right here, and it would prevent someone from overriding the return address without also overriding the canary, right? With the intuition being that before the system actually jumps to the red address, it can check to see if the canary has been changed in a way that's incorrect, right? So that's how the canary works. But can we get around the canary? Can we guess the canary somehow? Well, we can actually, if we make a few assumptions about how the system works. So, how do we defeat those canaries? So the first thing that we want to assume is that the server, it has to have a buffer overflow vulnerability. The second thing that we're going to assume is that the server is going to crash and respawn, just restart, if we set the canary value to a bad one. And the third thing that we're going to assume is that after the restart, that the canary and any address space randomization that you're doing is not re-randomized. Right? So what that means is that we're going to assume that if we can somehow crash the server, then when the server restarts, it's going to have the same value for the canary, and it's going to have the same locations for all the quote-unquote randomized stack, heap, and code information that it has. Right? So you might wonder, why would this be the case? Right? Why would it be that when the server comes back, it doesn't have new locations for things? The reason is because a lot of servers are written to use fork, right, to create new processes. And if you remember, fork actually inherits, sort of the child inherits the address space layout, right, of the parent, right? And it uses copy on write pages to change stuff as the child updates things. But if you use fork here instead of just executing a whole new process, anytime that parent server process spawns new children, those children will have the same values for the canary and the address space. Okay? So these are the assumptions that we're going to make to try to defeat these canaries here. So, how can we defeat the canary? Well, the attack is actually fairly straightforward. So imagine that the stack is going up this way, right? Imagine you got the buffer overflow here, and imagine that the canary is up here, right? And the canary actually has multiple bytes, right? So what you can actually do is you can probe those bytes one by one and start guessing values what those bytes are, right? So let's say that, sort of the canary sort of looks like this. Here's the overflow buffer, and you want to guess what these bytes are. So the first thing that you guess is you take your overflow just to this first byte of the canary, and you say, hey, is that byte 0? You write a 0 there with your overflow. You're either correct or you're incorrect. If you are incorrect, then the server is going to crash, right? If you are correct, you say, aha, I actually know the first byte of the canary, right? Then you start guessing here. You say, are you 0? Probably not, it's going to crash. Are you 1? And maybe not, it's going to crash. Are you 2? Aha, it doesn't crash. Right? So now you've actually found the value of that second canary byte. Right? If you can imagine, you sort of step up this way, and you eventually find all the values for the canary. Right? So once again, we're taking advantage of the fact that crashes are a signal to you, the attacker, that you've actually done something wrong. Right? And the server staying up, in other words, that socket connection staying open, is a signal to you, the attacker, you've done something right.
Maybe I missed something basic here, like why do you, if you know how long the canary is, can you just index directly, skip that buffer, and overflow the one after the canary? So like, because in C you can like index it like far above the canary.
Yeah, you can't. So that's right. If you in fact know the exact location of the canary, right, that can sometimes allow you to skip some of these attacks totally, right, because then you can just directly write to the return address, let's say, as opposed to sort of doing some of this buffer overflow nonsense. But in general, if there's some level of randomization here, if you don't quite know where the stack is, for example, then it's tricky to do that, right? And so basically the way that the attack proceeds is that you don't quite know what's happening, and so you just sort of very slowly creep your way sort of up memory, down the stack to figure out where these things are.
Can the server, instead of crashing when it finds the wrong canary, keep the socket open and spawn a new process and attach the socket to that process and make the first one?
Yeah, so we'll discuss at the end of the lecture some of the defenses you can have against this. But one very sort of abstractly speaking simple defense is that when the program crashes, you catch the seg fault using a signal handler. Do not do this in your own code, by the way. But you can do this, right? You catch that seg fault, and then the signal handler just kind of keeps that process alive for a bit, and that'll trick the attacker into thinking that, I won't get that signal back, in other words. Okay, so that's basically how you can guess the value for the canary. And note that you can actually use this attack to sort of figure out arbitrary values that are lower in the stack, right? Just by sort of iteratively guessing for each byte what it is, and then using that crash indication as a signal of whether your guess was correct or not. So that's basically how you can defeat these randomized canaries, assuming that after the server restarts, those things are not changed. And so we've also shown how you can use gadgets to sort of string together these more elaborate attacks. So what we're going to look at next is a way that you can use all of these techniques to defeat data execution prevention, address-based randomization, and canaries on a production system. Now what we're going to do now is we're actually going to start looking at 64-bit architectures instead of 32-bit architectures. As it turns out, for randomization purposes, 64 bits architectures actually give you a lot more randomness to protect yourself against the attacker. So looking at these attacks is much more interesting on those systems, right? And so that's also the type of architecture that's discussed in the Brock paper. They talk about 64-bit machines. So from now on, assume that we're going to talk about the 64-bit architectures. For the purposes of this discussion, the only difference between a 32-bit machine and a 64-bit machine is that on a 32-bit machine, the arguments are passed on the stack, right? So here, for example, this was like a 32-bit machine we were assuming. So for example, bash path was passed in a stack. On a 64-bit machine, the arguments are passed in registers instead. Okay, so like when a function starts execution, it's going to look in certain registers to find where the arguments are. Okay, makes sense? All right. So let's start up here. All right, so now we get to the point of today's paper, which is the blind return-oriented programming. So what's the first thing you want to do if you want to engage in ROP for fun or profit? So the first thing you have to do is you have to find what they call a stop gadget. Now, a stop gadget, right? And remember that when we say gadget, we essentially mean return addresses. right? A gadget is identified by the return address, by the start address of that sequence of instructions that we want to jump to, right? So what is a stop gadget? So a stop gadget is essentially a return address to some place in the code that if you jump to it, you're going to pause the program, but you're not going to crash it. Okay? So that's why it's called a stop gadget. Now, what might that stop gadget be? You might jump to some place in the code that then calls the sleep system call, for example, or does pause or something like that, or maybe somehow the program gets stuck in an infinite loop if you jump to that place. It doesn't really matter why the stop's happening, but you can imagine several scenarios which would cause that stop to take place. So why is this useful? Well, once the attacker has managed to defeat the canaries using that iterative guessing technique I showed you, he can start to overwrite this return address and start probing for these stop gadgets, right? And so note that most of the random addresses you might put there, they will probably crash the server, right? Once again, that's a message to you, the attacker. That's an indication that what you found is not a stop gadget, right? Because if the server crashes, your socket connection is closed. You as an attacker know, okay, that must not have been a stop gadget. But if you guess something and then that socket still stays open for a while, you're like, aha, I found that stop gadget. Right? So that's the base idea behind step one. You've got to find that stop gadget. Now, step two is that you want to find gadgets that pop stack entries. Right? And so you basically have to use this sequence of carefully crafted instructions to figure out when you've got one of these stack gadgets. So this sequence is going to consist of a probe address, a stop address, and a crash address. So the probe address is the thing that we're going to put in the stack. This is going to be the address of a potential stack popping gadget. This stop gadget is going to be what we found in step one. Right, so this is the address of the stop gadget. And then the crash gadget is just going to be the address of non-executable code. Right, and so for example, you could just set this to just the address 0. Right, if you do a ret to this and then try to execute code there, this is going to crash your program. Right, so we can basically use these types of addresses to find out where these stack popping gadgets are. So here's a simple example. So let's write this over here. So let's say we have these two different examples of a probe, a trap, and then a stop. Right? So let's assume that we have down here, we're going to probe at some address. Doesn't really matter. Starts at a 4, ends in an 8. That doesn't matter. Over here, let's say that we look at the address that, let's say, starts in a 4, ends in a C. So we're saying, we're hypothesizing that maybe one of these two addresses is going to be one of these stack popping gadgets. And then let's say that the trap up here, like I said, this is just going to be address 0. And then let's assume that we found some pre-existing stop gadget. At some addresses starts with 5, doesn't really matter. And remember that the stop gadget, like maybe this address points to code that does something like sleep 10 or something like that, right? So when I say that we're going to test these sequences, this is the stuff that we're going to push onto the stack, right? So similar to over there, when we were pushing these gadgets onto the stack, this is the stuff that we're going to push onto the stack, and then we're going to see what happens, right? Now let's say that that this code here points to the following sequence. We're going to pop some register, let's say racks, and then we're going to return. So what's going to happen here? Well, so when the system jumps to this address, the stack pointer is going to move here. Okay? Now we're in the middle of this gadget, right? What's the gadget going to do? It's going to pop racks, okay? Top of stack pointer is now here. Then it's going to return to whatever's the top of the stack, which is the stop gadget, right? So in this case, this gadget gets us to here, and the attacker can tell that this probe address belongs to one of these top stacking things, right? Because the client connection stays open, right? Now let's say that this gadget here pointed to something like the following. Maybe it just does like an XOR, for example. So it's just going to XOR some registers, and then it's going to read. So what happens if we try to jump to this gadget, right? Note that this does not pop anything off the stack, okay? It just changes the contents of registers. So what's going to happen? So we're going to be here. We're going to jump to the address of this gadget. Stack pointer goes here, okay? We're going to XOR these two things, right? Stack pointer is not going to change. Then we're going to return whatever the top of the stack is, which is 0, 0. This is going to crash, okay? The client connection to the server is going to close. And as a result, the attacker knows that this is not a stack popping gadget. So does that all make sense? And so you can also imagine that you can sort of, by coming with more sort of Baroque series of traps and stop gadgets and stuff like that, you can find things that, for example, pop two things off the stack, right? You just put another one of these trap instructions there, right? And so then, unless this gadget pops two things off, you're going to end up on one of these traps, and your code execution is going to blow up, right? And so in the paper, they discuss like this thing called the ROP gadget, which is sort of like hilariously complex if you're not used to returning to programming. What I'll show you today is you can actually just use these very simple pop gadgets to launch the same attack. And hopefully, after you understand this, the BROP gadget will make more sense. But does everyone understand how we can sort of probe for these little gadgets here? Okay. So once you've got these gadgets, what do you know? Well, you found the location of code snippets that allow you to pop stuff off, one thing off the stack, precisely one thing off the stack. But you don't actually know into what register they're popping it into. You just know that they're getting popped off, right? And you actually need to know what register these gadgets are popping stuff into, because remember, on a 64-bit architecture, the registers control, where the arguments are to this function that you want to invoke, right? So the ultimate goal to keep in mind is that we want to be able to create some gadgets that allow us to pop values that we put on the stack into certain registers. Then eventually we're going to call a system call that's going to allow us to do something evil. Okay, so the next thing that we need to do is determine which registers the pop gadgets use. So how are we going to do that? Well, basically, we can take advantage of the pause system call. Okay? So the pause system call, it takes no arguments, right? And that means that it ignores everything in the registers. Okay? And essentially, to find the pause instruction, what we can do is we can chain all of these pop gadgets in such a way that we put all of them on the stack. In between each one of them, we put the syscall number for pause. And then we see if we can actually get the program to hang. So let me give you a concrete example of that. So we'll do something like this. So here for the return address, we'll put the following. So let's say we have one gadget that pops RDI register, then does a ret. And then up here, we'll put the syscall number for pause. And then let's say that we have another gadget that we found that does a pop into a different register, let's say RSI. And then we'll put the system call number for pause up here again. And we do this for all the gadgets that we found. And then eventually we put the guest address for pause. Or sorry, for syscall, excuse me. And once again, remember how you invoke these system calls. So you basically have to put the number of the system call into the RAX register. Then you invoke this libc function syscall, which is then going to execute the requested system call. Okay. So what's going to happen when we execute this code, right? So we're going to come here. We're going to jump to the address of this gadget. Now note that as an attacker, all that we know is that this gadget here pops something off the stack. We don't know what the register is yet, right? I put it here just to make it clear, but the attacker doesn't know yet, right? So we jump, we jump to the gadget. The stack pointer is now here. What's it going to do? It's going to pop the syscall number for pause into some register the attacker doesn't know. And then we're going to continue to go up this chain, so on and so forth. And what you'll see is that each one of these gadgets, one of them hopefully will pop the system call number into the appropriate RAX register. So that the time we get up to here, I mean, we basically polluted all the registers, right, with the system call number. But hopefully just one of them has to be correct, right? Because if one of our gadgets does this, then by the time that we read to here, we will get a pause. Once again, that pause acts as a signal to the attacker, okay? Because if this guessed address was wrong, then probably the program is going to crash, right? So what does this phase of the attack let us do? Well, we still don't know which gadgets pop into which registers, but we know that one of them is popped into RAX, which is the only one to control, and for sure we know the address of syscall, right? Because we were able to induce the pause, right? So once we've done that, right, once we know for sure where this thing is, the address for syscall, then we can actually just try the gadgets one by one, right, and see which one of them is actually going to induce the pause, right? So in other words, cut out all the middleman here. We'll just have a stack that looks like this, and then you just immediately jump to syscall. Did that cause the pause, or did it crash? If it crashed, okay, we know this gadget, it pops the RDI, for example. Okay, get rid of that one, right? Try the next gadget, right? Put the guest address, well, it's not guest anymore. Put the real address for syscall up here. Were we able to pause the program? Yes? Aha. So we know that that pop gadget must pop into RAX. So does that make sense?
So the way to guess the address for system call is just blind attack.
Yeah, so in the paper they go into some optimizations about how you can look in the PLT and all that kind of stuff. Like I said, I think it's easier to ignore that for a second and just look for the simpler thing first. But yeah, in the simple attack that I'm describing, yeah, you just put some address up here and you just see if you pause. So does that all make sense? Okay, so at the end of this, we actually know the location of syscall. We know the location of the instruction that does the pop into RAX. Now you can imagine that we also need gadgets that pop into some other registers too, right? And suffice it to say, you can do similar tests, right? So instead of like pushing the system call number for pause, push it for some other command that now takes in arguments in RAX and RDI, for example, right? Do the same type of test, right? So basically, you can leverage the fact that for any particular set of registers that you want to be able to control, there's some system call that will give you a signal as an attacker that will allow you to figure out whether you've successfully invoked it or not, right? So at the end of this phase, you basically have the address of syscall and the address of a bunch of gadgets, which allow you to pop into arbitrary registers. Okay, and so now, let's see. So step 4 is going to be to invoke write. Right? Step 4 is invoke the write system call. So to invoke write, we need to have the following gadgets. We need to be able to pop RDI. We need to be able to pop RSI. We need to be able to pop RDX. Pop RAX. And then invoke syscall. Right? And so as it turns out, what are these registers being used for by system call? So this is the socket, or more generally the file descriptor that you're going to pass into write. This is the buffer. This is the length of that buffer. This is the syscall number. Right, and then you just call syscall. Right? So if we found all of these gadgets, then we can actually now control the values that are put into those arguments, or put into those registers, because we just push them on the stack, right? And so, for example, what's the socket going to be? Well, once again, we have to do a little bit of guessing here, right? We can take advantage of the fact that Linux restricts the number of simultaneous open file connections, or file descriptors to 1024, and also it's supposed to give you the lowest one available. So we do a little bit of guessing here, figure out what that socket is, put it in there. Now, interestingly, what are we going to pass in for the buff pointer? Right? We're actually going to use the text segment of the program. We're actually going to pass in the pointer to somewhere in the code of the program. So what's that going to allow us to do? That's going to allow us to read the binary out of memory using the write call to the client socket so that the attacker can then take that binary, analyze it offline, right? Just use GDB or whatever to figure out where everything's located. The attacker knows that now every time the server crashes, it's going to have the same randomized set of things in it. So now, once the attacker can find out addresses and offsets for stuff, now the attacker can directly attack those gadgets, right? Directly attack other vulnerabilities, figure out how to open up a shell, so on and so forth. So in other words, at the point you've exfiltrated the binary to the attacker, you've basically lost, right? So this is essentially how the BROP attack works. Like I said in the paper, there's a bunch of optimization, but really you need to understand this stuff, the basic stuff, before those optimizations can start to make sense. And so we can talk about the optimization maybe offline if you want or after class, but suffice it to say, this is the basics of how you launch that BROP attack. You've got to find the stop gadget, find those gadgets that pop stack entries, figure out which of those registers those gadgets pop into, and find out how to figure out where syscall is, and then invoke write by accumulating all that knowledge. So very quickly, how do you defend against BROP? Well, the most obvious thing is you got to re-randomize, right? So the fact that crash servers do not respawn re-randomized versions of themselves, that allows the crash to sort of act as a signal that lets the attacker sort of test various hypotheses about how the program's working. So one simple defense is to make sure that you do exec when you spawn a new process instead of fork. Right? Because when you exec the process, you create a totally new randomized layout space, at least on Linux. Right? So on Linux, when you compile with this PIE, the position-independent executable flag, you only get that randomized address space that's new if you use exec. So another defense you can use is just use Windows, because Windows basically does not have a fork equivalent. Right? So hooray for us. So that means that on Windows, whenever you spawn that new server, it's always going to have a new sort of randomized address space. I think someone over here mentioned something like, what would happen if, for example, when the server crashed, it didn't actually close the connection, right? So you can imagine, once again, that when the crash takes place, we somehow catch that fault, and then we keep that connection open for a little while to confuse the attacker and remove that signal that something is going amiss. So that's something you can definitely do, but what's hilarious about that is that now your BROP attack turns into a denial of service attack, right? Because now you just got all these potentially zombie processes that are sitting around, they're seg-faulted, they're useless to society, but you can't let them go because otherwise they're going to leak this information, right? Another thing you might think about too is you could do bounds checking, right? We just talked a bunch about that, right? But in the paper they sort of casually dismiss this as saying, it has like a 2x overhead, so nobody's going to do that, right? But you could, in fact, do that. So that's basically how BROP works. As for the homework question, the homework question was a bit subtle, because the homework question says, what if you use a hash of the current time, right, get time of day, when you restarted the program? Is that sufficient to prevent this type of attack? Well, note that hashing does not magically provide you bits of entropy if the input to the hash is easily guessable. Right? Like if I know that you're only going to hash one of two things, it doesn't matter if I have like some, a jillion-bit hash. It doesn't matter. So I can just guess one of those two values and see what it is. So the thing to note is that get time of day actually has much less entropy than you might think, particularly because the attacker can actually check what time he or she is launching the attack. right? So that's going to actually remove a bunch of the entropy from that calculation, right? And so there's, some subtleties there, what's the server skew in terms of clock of the client, so on and so forth. But long story short, using a guessable base value, even if it's guessable just inside of a range, is super useful for the attacker, right? Particularly because the attacker can start subverting a bunch of servers in parallel and know that all of them should have fairly similar values, right? At least in the higher order bits, right? So long story short, the answer is that, it's literally better than nothing to randomize, using the get time of day, but it doesn't actually provide you as much security as you think. And the other lesson too is that just because you hash something, right, that doesn't matter if you're not actually sort of using that hash in a smart way. You have a question?
Yeah, so when I did the calculations based on them saying that the attack would take about 20 minutes and you could expect to have 8 hours, it seems like you need to be able to get the offset between your clock when you lose the socket and their clock when they restart the process to within like 48 milliseconds.
Yeah, so getting the timing right depends on a bunch of different things, right? But you can take advantage of the fact that the attacker can open up a bunch of connections in parallel and leverage the fact that even if the initial guess is a little bit off, you can still launch multiple guesses on what should be very similar canary values and sort of do that attack in parallel. But you're right, there's tricky timing issues. Okay, so yeah, we're going to close up now. If you have any questions, come talk to me afterwards or post on the